We're now ready to take a look at the exponential distribution. We've taken a look at the uniform distribution, and we've assumed therein that situations that that ask for the uniform distribution have outcomes that are all equally likely over a given interval. Now, that's not necessarily always true. And in some other situations, we might want to model with the exponential distribution, which is often used to model the likelihood of an event over some duration of time. So a lot of times when you think about warranties and how warranties are priced, like let's say on a laptop, a portable device of some sort, or even car tires for a vehicle, they tend to follow an exponential distribution. It's a pretty solid model. And what it amounts to is that in an exponential distribution, this is a decaying distribution, you get a lot of small values or small times and very few big times. So in the event of a laptop, what you might notice is that if you were modeling how long the laptop lasts, and this is some measurement of time, and then we deal with density because the probability of something ultimately breaking down is 100%, or so we assume. And so we see something that looks like this, which tapers down and eventually comes down to 0. That is, everything ultimately fails. We assume that about it. And you can see that a lot of the time, so if these were spaced by 1, you would see that I could argue here that but up to time 2 in this situation, most of my area is accounted for. In fact, even if we maybe went out to time 3, you can see that most of the area under that curve is going to be accounted for. So if this were how long laptops last, then most of them would break down within 3 years, and very few would go on to last a lot longer. So if we think about this as the density corresponding to breakdown times, or even a new set of car tires, maybe, car tires are going to last 3, 4, 5, 6 years, but you're going to have very few car tires that last longer than that. Now, it doesn't have to be that time is along the horizontal axis. You could also have situations where, like, for example, the amount of money spent on groceries, that if people go into a grocery store, a lot of them spend very little. So imagine that instead of time here, we had the amount spent. And very few people are going to spend a lot of money, but let's face it, a lot of us will go into a store and we just needed a box of Q-tips that cost $2, or maybe a pack of floss that cost 99 cents, and we leave. So a lot of us spend very little, few of us spend a lot. And that's the exponential distribution in a nutshell. There are many small values, few large values. And when this model is used, this deals with measurements of reliability. This is kind of a natural distribution that is used for the purposes of looking at, for example, longevity of time, or even time till an earthquake occurs. We could look at probability distributions based on data we've collected. So in general, like we've already kind of drawn here, we have density, and then we have some measurement, which could be time or amount spent, and we get a decaying exponential function. Now, to have a decaying exponential function, we've seen examples of these in algebra before, like, for example, 2e to the negative 0.1x. Now, for x bigger than 0, x is greater than or equal to 0, this quantity right here, if you raise a value to a negative number, that's the same thing as writing 2 over e to the positive 0.1x. And so as x gets bigger, e to the 0.1x gets bigger, which means this denominator grows, and so this whole fraction right here goes down, it decreases, as long as you have a decay rate. If that number in the box there, if that were positive 0.1, you would actually see this function growing, and that's not what we want when we're modeling these types of situations. Again, we're looking at many examples of small values and few examples of very large values. So then what this boils down to is we're going to have to estimate this decay. This is a decay rate. And of course the decay rate will depend upon context. So for example, if we're dealing with something like, let's say, an air conditioning unit in a house, well, that's going to last maybe 15, 20, 25 years. And on the other hand, if we look at something like a battery-powered fan, one of those little fans that you could buy that is like a personal mini fan, that's probably going to have a longevity if you use it often of maybe a couple of months, maybe a couple of years if you're really, really lucky. So this decay rate is just going to depend upon the context. Now, one of the stipulations is that we need this area to be 1. And we're also going to define an exponential distribution for a random variable x with decay parameter. This is called lambda. This is a Greek symbol. We often use Greek symbols to represent constants. And also what we'll point out here, okay, so if it has a decay parameter of lambda, that's this number here, then we're going to say x is distributed exponentially with parameter lambda. Okay, and also we should point out that x is in the interval, I'll write it like this, is in the interval from 0 to infinity. Okay, you can't include infinity, that's why we don't have a square bracket there. You can never get to infinity, but this curve basically goes on forever. It just gets very, very close to 0, and you're not getting very much area after the input axis gets really large. Okay, so we write that x is exponentially distributed with parameter lambda. Now, how do we find this function here? Well, it's going to be lambda e to the negative lambda x. Well, why is that? Well, it's because the area under this curve has to equal 1. So let's just briefly show that if you take from 0 to infinity, if you take the antiderivative of e to the negative lambda x dx, just for some illustrative purposes here, the antiderivative here will be negative e to the negative lambda x. That will be the antiderivative, and we look at this function from 0 to infinity. Well, if you evaluate this thing at infinity, and I'll just go ahead and write it as e to the negative lambda times infinity, minus negative e to the negative lambda times 0, well, we've already described this, that if you raise a number to a very large negative power, this is going to be very, very close to 0. And if you take e to the 0, that's equal to 1. You have minus a negative 1, which is positive 1. So the reason that this lambda appears out front here is when we take the antiderivative. You can check our work here. Take the derivative of negative e to the negative lambda x, you get, by the chain rule, negative lambda times negative e to the negative lambda x. Our negatives cancel, and you can see that that just gives us lambda e to the negative lambda x. Now, we won't derive these, but there is a mean and a standard deviation, and they both happen to be the same. So the expected value of x, or we could call that mu for mean, is equal to 1 over lambda, and the standard deviation of x, or sigma, is also equal to 1 over lambda, which is kind of nice. So if for example, we had a negative 0.1, then for this situation, mu would equal 1 over 0.1, so the mean would be 10. Maybe that's 10 minutes, 10 years, 10 months. That would give us the average amount of time before something breaks down, and also with, in that case, a 10-year standard deviation as well. In the next example, we'll take a look at working with these. We could again derive the expected value and the standard deviation, but we won't do that here. That would involve getting into some more complicated integrals, but we can trust that this is what would happen. So we'll take a look at examples next.